All right, good morning, everyone. Welcome back to class. It is the 19th of September. We're finishing up the 5th week of the semester. It's kind of hard to believe that. So we're basically about a third of the way done with the semester already. So we're all done with the first exam. You should have gotten your exam back in Canvas. If you haven't gotten that, let me know. I posted the key as well. So just let me know if you have any questions about your exam score. We can definitely talk about that. So we do have another exam. It's about a week and a half out. Exam 2 will open at the end of the month, so Monday the 30th. And just like the first exam, it'll be open for 3 days until the 2nd of October. That exam will cover Chapter 3, which we're working through right now. Are there any questions out there? Anything you want to ask me about the exam coming up, about projects, homework, anything at all that you're curious about? We're doing well on time, so we can definitely take a few minutes and talk about anything you'd like. So, chapter 2 was mostly about hypothesis testing, right? We were testing the population parameter P, and we used a randomization applet to do that. Basically, it comes down to flipping coins. We're flipping coins to see if we could get evidence against a null hypothesis, right? And that's great. Randomization is a very respected and commonly used technique, but there is another route, another tool for finding p-values for hypothesis tests, and that's using the normal distribution. Okay, and honestly, it's probably more common to use the normal distribution than the randomization applet. So it's kind of like the most common way of doing hypothesis testing. So that's where we're at. We're trying to get to where we can use the normal distribution to do inference, to do hypothesis testing and later confidence intervals. So for us to be able to do that, for us to be able to understand what we're doing when we use the normal distribution, we have to understand the sampling distribution of p hat, right? When you do a hypothesis test, say a hypothesis test about about p, right? You've got a null, you have an alternative, and it's p equals some value, maybe 0.5, and then p not equal to 0.5, right? Maybe greater than 0.5, right? So we test it by using p hat, right? So before we would take p hat and then we would do the simulated null distribution, which is basically a normal distribution, and then we would count the dots. So it's all about this distribution of p hat. Okay, so we take p hat and then we make a decision based on p hat, right? The p-value associated with p hat. And so the only way we can make sense of that with the normal distribution is to understand that p hat can be approximately normally distributed. Okay, so I told you that, and now I want to kind of look at some real examples of why that would be the case. Okay, so so if p hat is normally distributed, then it will have a mean, right? So we call that mean mu sub p hat, and it's equal to the population proportion. So this is the mean of the normal distribution, and then every normal distribution will have a spread. It'll have a standard deviation. We call that the standard error, and it's given by this expression here: square root p 1 minus p over n. Okay, so these two facts are here on your formula card. Okay, they're right here. The mean and standard deviation of the sampling distribution of p hat. Okay, so the middle of the distribution will be the population proportion, and the spread in the sampling distribution of p hat will be that expression there. Okay, so we're going to take a deeper look at this expression here and just verify that it actually works. So the lecture notes are good for this section, but I have another document that I like to use. I think it's just a little bit, it's like a supplement to the lecture notes. And so let me put this in the chat. So if you'd like to download this, I'll put it in the chat over here for you. And later, if somebody will remind me, I will also put this on the Canvas website. But let me just go ahead and, oops. See here. Okay, so look over in the chat. If you want to download this document, you can. If you don't want to download it, I think it's, you could probably, it's all right. But what is it? We're looking at the sampling distribution of p hat. So basically, if we're going to make a decision based on p hat, then we really need to understand how p hat behaves, right? And so that's what the sampling distribution allows us to do. What we do is we actually generate all the possible p hats and we look to see how they behave. Okay, and then once we understand its behavior, then we can use it to find a p-value. Okay, so the example is this. Let's say you are a quality control engineer at the M&M's plant in Cleveland. Okay, so M&M's do have a plant, one of their main plants in Cleveland, or at least they used to when I put this this worksheet together. And M&M's come in different colors, and one of the common colors is orange. Okay, so one of the things they do is they have a target for how many orange M&Ms they want to have. Right, so at their Cleveland plant, and you can look this up, I found this in a real paper, the target proportion, the target percentage is 21%. So in other words, they want to have 21% of their M&Ms being orange. Okay, now for some reason that I don't know, I don't understand their reasoning here, but at a different plant in New Jersey, their target percentage of orange is 25%. Okay, so there's two different plants, and so basically it allows us to do this exercise twice. We're going to do it once for Cleveland, and then if we have time, we'll do it again for the New Jersey plant. Okay, so we're going to pretend first that we are at Cleveland. Okay, so we're managing the factory there in Cleveland, and the target is 21%. Okay, so what we're going to do is use our applet to generate all of the possible p hat values. Now it's the same applet, but it looks a little bit different. It's designed with M&M candies in mind, which is kind of fun, right? So what you want to imagine here is we've got thousands and thousands, millions of M&Ms that are being produced at this plant in Cleveland. Okay, and let's say things are working as they're supposed to work, and we've got 21% orange M&Ms. Okay, all right, and then so how do we know that everything is working correctly? Well, we take a sample, right? So so let's say every day we take a sample of 50 M&Ms and we look at the proportion that are orange, right? See how things are going. I think that sounds pretty reasonable. Okay, so let's take a sample of 50 here. Okay, and so if I take a sample of 50 and everything is working correctly, how many M&Ms should be orange? Okay, so let's go back over to our sheet over here. And that's the question here. If you take a sample of 50 and everything is running as it should, how many orange would you expect? Well, we have 50, which is N, and then it should be 21% as orange, right? So what is that? That's N times P, right? So if I go 50 times 0.21, it gives me about 11. Okay, so just let that sink in for a second. If you take a sample of 50 with the goal of doing some quality control and just making sure that the proportion is 21%, you would expect about 21, right? Okay, so actually you expect about 11, right? Because that's 21% of 50, right? So let's see what happens. Okay, so here we're actually going to do a sample of 50. Okay, so you can see just as this nice little candy animation here. Look over on the left. You see the orange ones that have been selected? Okay, so there's 50 total, and then it just took all the ones that ended up being orange and put them over here on the left. Okay, so how many is that? It looks like 16. Well, let's count it up. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it looks like 8 were actually orange. Okay, so we have 8 n is 50 for a p hat of 16, proportion of 0.16 or percentage of 16%. Does that make sense? Did you guys see that? So let me go back again. And so again, we did one sample of 50, and of those 50, 8 ended up being orange. Okay, so 8 out of 50 is 16%. We were expecting 11, we got 8. Is something wrong here? What do you guys think? Would you call your main technician and tell them to shut down the plant? Or, do you find this result disturbing, or do you think this is kind of expected? Okay, so we were expecting 11, we got 8. It's supposed to be 21%, but we got 16%. I think the answer is we're not really super surprised by that, right? So let's see here over in the chat. Yeah, we expect, great, Armand, you're exactly right. We expect some variation from 11. 11 is if there's exactly 21%. But this is a sample, right? We're not looking at all of the millions of these, right? We're simply doing a small sample. So yeah, we're not gonna stop the production run, right? That costs a lot of money to shut down the machines, right? So maybe we'll do another sample, but we're not convinced that things are going awry yet, right? So let's do that again. So I'm going to come over here and I'm going to hit the sample again. So we draw another sample of 50, and this is a lot of fun because you can see the animation there. Okay, this time we get another 50, and let's see, let's count the orange M&Ms over here. 1, 2, 3, 4, 5, 6, 7, 8. We actually got 8 again. Okay, so we got 8 out of 50 for a percentage of 16% again, right? So 8 out of 50 for a percentage, a sample proportion of 0.16 again. So what do you think? Do we need to shut down the plant, or does this seem okay? So we actually did get P1 equaling P2. I'm going to go out on a limb here and say that you guys are not surprised by this. Okay. Yeah, we get 8, we get 12, we get 9. These are not weird values. We get 8 and 8. Okay, maybe I wasn't expecting it, but it doesn't really indicate that anything's wrong yet, right? If we get 50 out of 50, or if we get 0 out of 50, definitely something's wrong, right? But 8, 9, 12, these are okay. Okay. And so the sample proportion will vary from sample to sample because of randomness. But we don't expect it to get too far away from 21%, right? So we expect numbers like 20%, 23%, 16%. These are reasonable, but we don't expect 100% or 0% or even like 80%, right? So what we can do with this applet is get a really good idea of how much p hat bounces around, right? And we talked about this before, right? We've used this applet to give us an idea of how much p hat can vary. So let's do this 5 more times. Okay, so I'm just going to hit the button 5 times. We get 5 more dots. So 1, okay, that time we got 10%. Okay, this time we got 16%. Okay, now we finally got something more than 21%, right? We expect it on both sides, right? So there we go. We've done it 5 more times. And so if you look at the values down here, the middle value should be about 21 because that's the population proportion. We get some that are above. We got 24%, and then we got something all the way down to 10%. So this is giving us an idea of how much we would expect p hat to bounce around, right? So, if you go in there, you do a sample and it's 24%, it's probably okay. If you get 10%, it's probably still okay because you can just get that p hat bouncing around just, because of randomness, as we see here. Now, to speed this up, we don't want to sit here and hit the button all day, right? So I'm going to go to 200 samples, each of size 50. And then we should get a really nice idea, I think, of how much p hat can bounce around just by chance. Okay, so the biggest p hat we got was 36%. The smallest was about 6%. Okay, so this gives us an idea of kind of the the expected amount of variation in p hat. Okay, so if you get anything below 6%, then that's kind of weird. If you get anything above 36%, that's probably also weird. But anything in between can happen, just by chance. Is this making sense? Okay, so what are we getting here? We're getting that null distribution that we've seen over and over and over again. And, now that you've worked with a normal distribution, you know that this is probably a normal distribution. Okay, it is, or it will be. Okay. Okay, so describe the pattern of the histogram. Well, we have more or less one peak in the middle, and then on the right we have a tail that decreases, and on the left we have a tail, right, that decreases. Okay, good. So now what we're going to do is, instead of 5 rounds of 50 or 200 rounds of 50, we want to look at all possible p hats. Okay, so how many different samples of size 50 are there when you have millions of M&Ms that you're producing? Well, there's actually a ton of different samples of size 50. The numbers are so large, it's hard to even know what the name of the number is. I mean, it's like billions of trillions of possible samples of size 50. So software is fast, but it can't do all of them. So what we're going to do is we're going to approximate the sampling distribution by doing 10,000. You can do 10,000 samples of size 50 with software. So what we're going to do is we're going to approximate the sampling distribution, and we're going to do that by setting the number of samples to 10,000. So with one click of the button, we're going to get 10,000 samples, each of size 50. Okay, and what this will do is it'll approximate our sampling distribution. This is approximately the same as the full sampling distribution. So more or less, this is what if you took all the possible p hats out there and you plotted them, it would look like this. Okay. And so what am I trying to do here? I'm trying to show you that, yeah, this looks like a normal distribution, right? If we turn on the normal distribution here, yeah, it's very close to the actual normal distribution. And I also want to look at the mean and the standard deviation. What's the middle of the distribution? 0.21. Is it a coincidence that the probability of orange is 0.21? No. If 21% of the M&Ms are orange, we would expect the middle or the mean of the sampling distribution to be the same thing. And that's what we see here, 0.21. The standard deviation is a little bit harder to pin down. It's a measure of spread, so we don't really have an intuitive value for that, but there is a formula. Okay, so let's take those two values and put them over here. Okay, so we have the mean of 0.21. Okay, so that lines up with what we'd expect there. And then the standard deviation, 0.057. Okay, all right. So let's calculate the standard error using our formula. So I told you the formula, now let's use the formula, right? So the formula is P times 1 minus P. So P is 0.21, so we're going to go 0.21, 1 minus 0.21. So 1 minus 0.21 is what, 0.79? Okay, and then we're going to divide that by the sample size. So each of those 10,000 samples has 50 M&Ms in it. Okay, so we go over to the calculator. Okay, so we have 0.21 times 0.79. Okay, then we divide by 50. We take the square root of that, and what do we see? 0.058. Okay, now we got 0.057 in our applet, but that's pretty darn close, right? I mean, to the second decimal place, that's correct. Yeah.
Yeah, I joined a few minutes late and
It's
I don't
not in this.
remember using the square root.
You don't remember? Well, I mentioned the square root at the end of class last time. This formula right here. So we're learning about this formula here for the standard error of p hat. So we,
Oh, okay.
this is the first time we've actually calculated it in class, but we did write that formula down, and I'm showing you how the formula works now with the square root in it. Does that make sense?
Yes, thank you.
You bet. Okay, so does everybody see that the theoretical value here is basically what the applet told us? Okay, now I bet if we did, instead of 10,000, if we did like 20,000, if we did this a couple more times, it would actually converge to the exact theoretical amount. So let's do that here. So I'll do a couple more. Yep, there we go. See? So I did 40,000, and now it is actually exactly the theoretical value there, 0.058. Okay. So what's the takeaway? What are we talking about here? The sampling distribution for p hat is approximately normal. The mean is the same as p. So the mean of the sampling distribution for p hat is equal to the population proportion, and the standard error, the spread, is equal to this expression here, square root p 1 minus p over n. Okay, so basically what we just did is we showed that these two formulas are correct. So let me show you again. Okay, maybe you think, well, 50 is a small sample size. Maybe if you're a quality control engineer, you would do a sample of 500, right? I mean, M&Ms are pretty inexpensive, and you've got a lot of them. Instead of 50, let's do 500. Okay, so imagine every day now your job is to go in there and you get a random sample of 500 M&Ms, and you find the proportion that are orange. Okay, so we'll do 500, and we want to simulate the sampling distribution. So we're going to do 10,000 rounds of 500 samples. I'm sorry, 10,000 rounds of a sample of size 500. Okay, so it's 10,000 times 500 candies sampled. Okay, so when I hit the draw samples here, it takes a minute, right? Because we're doing 10,000 samples, each of size 500. And what do we get? We get a pretty nice normal distribution. Okay, now it's got a few rough edges here and there, but if we did another couple of these, let's maybe do one more here. So now we've actually got 20,000, right? So it's a pretty nice approximation for the overall sampling distribution. Okay, so this is basically represents all possible samples of size 500 M&Ms. So there's lots of those, right? What is the mean, and what are the mean and standard deviation here for these two? Okay, so well, look at the mean there. It's 0.21. Yeah, just like we would expect, right? If 21% are orange, then when you look at all the possible p hats out there, you'd expect it to be about 0.21, and that's what we see. What about the standard error, the standard deviation? 0.018. Okay, so let's write those down and verify that with the formula. Okay, so we're expecting 0.21, which is what we got. And then the standard error from our applet there, so we're empirically seeing this, right, is about 0.018. So let's use our formula. So the formula says square root p1 minus p over n. So p is 0.21, 1 minus p, so 1 minus 0.21 divided by n. Here we're doing samples of size 500. Okay, so let's see here. So we'll go 0.21 times 1 minus 0.21. Okay, and then we'll divide that by 500. We'll take the square root of that, and what do we get? 0.018. Okay, so I love seeing the theory line up with, the empirical result, right? So the theoretical result and the empirical result are completely in agreement here, right? So 0.018 empirically, and then theoretically from the formula 0.018. Okay, so to me, that's very convincing, right? If you want to be more convinced, then you have to take a few semesters of calculus and work through the math of it. But basically, that's good for our class. Now, which histogram has more spread? The one here or the one up here? Well, remember, standard error is a measure of the spread. So if this spread is 0.057 and this spread is 0.018, then this one should have more spread. And we can see that, right? This one is going all the way from about 6% up to about roughly 40%. This one is actually much tighter. It's going from about 15% up to about 26%. Okay, so the one with a smaller sample size has more spread. Okay, so the n equals 50 has more spread. Why is that? Well, it's a smaller sample. If you have a smaller sample, it's easier to get kind of more extreme values. If you have a large sample, then those extreme values tend to cancel each other out. So you get less variation there. Okay, so super important result. Let me go ahead and go back to our lecture notes here for a little bit. So that's basically just what this is saying here. Okay, so the sampling distribution for p hat taken from samples of size n will be approximately normal when the data come from a random sample, they're independent of each other, and we have a large enough sample. Okay, so if it's normally distributed, it'll have a standard deviation, which we call the standard error, and it's given by that formula, and then the mean will be equal to the population proportion. Okay, this is known as the central limit theorem. Okay. All right. So down here on 93, the center stays the same each time, right? So as n gets larger, the center stays the same. It's always p. And then the spread gets smaller or less, right? We saw that the spread in the distribution decreases as the sample size gets larger. The shape becomes more and more normal. Okay, it goes from being less normal with the spaces between the columns and sometimes some skew to having little space between the columns and without any skew at all, right? So again, if we go back and look at this applet, if I turn on the normal here, we see that, yeah, it's quite normal. It does have a few rough edges here, but if we were patient and did even, like 30 or 50,000 samples, we would see that it would become even more and more normally distributed as time goes by. Okay, so, right, see that? So, good. Let's keep going. Now that we know how that formula works, we can use it. But are there any questions about that before we move on? Anything that you want to ask me? It's a big idea, okay? And so that's why we have homework, so you can practice with us. So let's practice. Okay, so let's come down here to the bottom of 94, and let's do some geographical research. Okay, so so out here in the western states, a lot of the land is federally owned. Okay, and so it turns out, at least when we wrote these notes, about 65% of land in Utah is federally owned. Okay. And so let's say, you're doing some geographical research. Maybe you're a GIS, graphical information systems analyst for, a petroleum company, or, or maybe you work for the government, and you want to do some research on land in Utah. So you're going to do a random sample. You're going to take a random sample of 100 locations in Utah. So how would you do that? Well, it's very easy with software, right? You take Utah, and then, so that's a terrible picture, but you basically divide it up into a bunch of polygons, right? Using software. Okay, so you can take Utah and you can divide it into 10 polygons or 10,000 polygons. Very easy with software. And then we would do a random sample from those, right? So each polygon would have a number, right? So that'd be 1, that would be 2, and then you randomly select 100. Does that kind of make sense? So we have these random lands, maybe this one, maybe this one, this one. You guys have done random samples, so you've got an idea of how this works, right? So here's our random sample of 100 lands in locations in Utah. And so what are we going to do with it? Well, we're going to, see which are federally owned and which are not. Okay, so each of these locations pretty much will either be federally owned land or not, right? So what kind of data is that? That's categorical. Most of what we're doing here in chapter 3 is categorical. So it's a yes or no. You get your list of 100 randomly selected locations, and each one will be federally owned or not, right? So it is categorical, which means the parameter we're thinking about is P. So it's the proportion of land that is federally owned, right? So it's the proportion of federally owned land in Utah. Okay, so you get your sample of 100 locations. If P truly is 64.9, if we think about all possible samples of size 100, each one would have a P hat. What would we expect the middle of that distribution to be? Well, 0.649, right? Okay, so again, the middle of the distribution should be the population proportion, right? That's what we just saw a couple times with our M&M's example. It's also here on the formula card. So the mean of the assembly distribution of p hat should be the same as the population proportion. That's a pretty obvious fact, I think, if you think about it. The spread is a little bit harder to predict, but we have a formula, so it's not bad. And the formula is P 1 minus P over N. So P is 0.649. N is 100. So we go to the calculator, not too hard. Okay, divide by 100. Take the square root, and we get 0.0477. So what does that mean? Well, when you take a sample of 100, it's just one small part of the whole population of locations in Utah, right? So we expect some variation there due to sampling error, but we do still expect it to be pretty close to 65%. So your typical distance away from 65% will be about 5%. So in your typical sample, it'll be somewhere between 70% federally owned and 60% federally owned, about 5%, within 5% of 65%. So if you get a sample that's like 90% federally owned or 10% federally owned, something weird has probably happened, right? Okay, what's the shape going to be? Well, the shape will probably be normal, but we can't just assume that it's normal. What we have to do is make sure that the 3 conditions have been met. Okay, so what are those 3 conditions? Sorry for the scrolling, but the list is up here. Okay, so we have to make sure that we have these 3 conditions met. The data have to come from a random sample. The observations have to be independent. And then we need a large enough sample. We need to have at least 10 successes and at least 10 failures. Okay, so we have to have randomness, independence, and then at least 10 successes, at least 10 failures. So do we have that? Well, let's look. We have a random selection. Okay, so it says random. 2, we have to have independence. What does that mean? Well, you don't want all of your land coming from one small part of Utah, right? Because there are large parts of Utah that are federally owned, and so you don't want all of your land coming from like the same region, right? You want it split up, and you probably don't want like two pieces of land that lie next to each other, right? So the rule of thumb is that the sample size has to be less than 5% of the population size. So we can express that with an inequality. Little n, the sample size, has to be less than or equal to 5% of the population size. Okay, so what is little n here? Little n is the sample size. So what is this saying? 100 has to be less than 5% of all of the locations in Utah. So how many locations are in Utah? Well, it's just however many locations you make with your grid there. So what does that mean? Well, we can solve this for capital N. So if I divide both sides by 0.05, so we go 100 divided by 0.05, 2,000. So what does that mean? I need in my grid over here that I'm going to create, I need to have at least 2,000 locations to choose from. So you set up your grid and you have at least 2,000 there. So if you have 2,000 or more pieces of land to choose from, then 100 should be small enough so that it's nice and spread out and you don't get a bunch of land, all, in one region of Utah. It's going to be pretty nicely spread out. Okay. The third thing we need to have is at least 10 successes and at least 10 failures. So how on earth do you figure that out? Well, how many successes are we expecting here? Well, we kind of answered that question in our activity over here, right? We said, okay, if p is 0.21 and the sample size is 50, then how many are we expecting? Well, we expect n times p. Right? I mean, if we have 100 randomly selected locations and roughly 65% of Utah's federally owned, wouldn't we expect about 65 of those to be federally owned? Yeah. So what we have to do is we have to say NP, that has to be at least 10. Okay, we need to have some pieces of land that are not federally owned. We have to have some that are federally owned. The rule of thumb is that if you have about 10 or more in both of those categories, then all of the math will work. Okay, so we go N, which is 100, times P, 0.649. That has to be more than 10. Well, yeah, it's about 65, right? Okay, so that's going to be fine. Then, so that's saying we need to have, at least 10 pieces of land that are federally owned. And then we also have to have some that are federally owned. If it's all not federally owned, then, I'm sorry, if it's all federally owned, then you don't really get a good idea of how much is not, right? So the other one that we have to look at is N times 1 minus P, right? 1 minus P tells you the percentage that's not federally owned, right? So that's going to be 100 times 1 minus 0.649. Okay, so let's see, that's going to be 1 minus 0.649, right? So yeah, about 35% is not federally owned, right? So we go times 100 here. And so we would expect about 35 pieces of, 35 of those locations to not be federally owned. So what does that mean? We have a large enough sample. Okay, so these three things tell us that the shape will be approximately normal. Okay, and we know what the mean and the standard deviation will be. So how does that help us? Well, we can make predictions about our sample. Okay, if we know that the sample is coming from a sampling distribution that's normally distributed, then we can use the normal distribution to make predictions about it. Okay, so let's do that. Okay, so I'm going to draw the normal distribution, and I'm going to say something that's a slight exaggeration, but only slightly exaggerated. For the rest of the semester, on pretty much every problem, you're going to draw a normal distribution. So just get in the habit of drawing a nice normal, finding your mean and your inflection points, and shading in the relevant region. Okay, so that's the middle. So your typical sample is going to have about 65% federally owned. Then we need to go out one standard deviation in both directions. Okay, so if I go 0.649, the mean minus the standard deviation, which is the same as the standard error, that gives us what value? Let's see here. So 0.649 minus 0.0477, 0.6013. Okay, so 0.6013. So where is that? That's at the inflection point. That might be about right there. Right? Remember the inflection point, that's where the standard deviation is. So that's about 0.6 right there. And that's actually what it's asking. Right? What's the probability that p hat is less than 0.6? So that's nice. It's right at the inflection point. So with it, this isn't even a great graph, but it's okay. Just by looking at that graph, I can guess that it's about, I don't know, 20%. Does that look like about 20% of the distribution? But we don't need to guess because we can use GeoGebra, right? So let's run over to GeoGebra and ask GeoGebra for the percentage. Okay, so we open up GeoGebra. We're going to go to the toggle, the three dots, probability calculator. Okay, so we put in the mean, which is 0.649. We put in the standard error, 0.0477, and we want to say less than, and then less than what? Well, 60%. Okay, so how likely is it that you take a sample and it's less than 60% federally owned? Well, it can happen. It's not likely, but it's not unusual. It's got about a 15% chance of happening. See that? So it's 0.1522. So 0.1522 there. So that is the probability of your sample having less than 60%, whoops, federally owned. Darn it. A little bit unlucky there. Well, so what's the probability then that more than 70% is federally owned? Let's do that one. That's what this is saying here, right? So now we're going to take a sample. And before we do it, what's the likelihood that more than 70% of that land would be federally owned? Well, it's very easy with GeoGebra. Okay, so 70% is actually at the other inflection point. So 70%, I'm going to be lazy and use this diagram again. 70% is actually at the other inflection point. So we just found that other value was about 15%, so it should also be about 15%. But we don't need to guess because we can use GeoGebra, right? So we're going to come over here and we're going to say greater than 70%. Okay, and yeah, we get about 15%. It's 0.142. 0.142. You see how useful that is? I mean, we can make predictions about our sample. That's, a big part of what stats is all about, right? We have samples and we're trying to use the sample to make inference and kind of educated guesses about the population. So knowing that it's normally distributed is very, very useful. In fact, it's kind of the foundation for how sampling works. Okay, so if you're following, say, the polls for the election, that's basically what they're doing. They're taking samples of maybe size 1,000, and those samples come from a normally distributed sampling distribution. Okay, so then they look at the sample and they can use the normal distribution to make a guess, right, about what's actually going on in the full population. Okay, let's do another one of these because, I'll be honest, this is probably the most complex thing we've done all semester, at least mathematically. So it definitely helps to do a couple of these in class. So let's do another one that's very similar. It's basically the same exact idea, but different context. But before we move on, let me just ask you guys, do you have any questions about this? Let's do another one then. So the next problem is basically the same exact idea, but instead of doing geographical research, let's say we're doing economics research. Okay, so one of the branches of economics is developmental economics. So they're looking at the economies in developing countries. And so let's say maybe we're going to travel to this country where 28%, it's more or less known that about 28% of adults do not own a cell phone. Okay, and so you're doing some kind of research there, and cell phone use is that's relevant to the economy, right? So you're going to do a sample of 200, and we want to think about what the sampling distribution for p hat is. So first of all, what kind of data are we collecting? Well, each adult either owns a cell phone or they don't, typically, right? So either you own a cell phone or you don't. So it's definitely a categorical type of data that we're looking at, which means it's P. We're thinking about P. Okay, and so what is that? What is P here? P is the proportion who do not own a cell phone. So it's the population proportion of people, adults, who do not own a cell phone. So, country probably has at least a few million people in it, so you can't talk to everybody. So you take a sample, and then so in that sample, you talk to each person and you say, hey, do you have a phone or not? You own a cell phone? They say yes, they say no. And then you get your p hat, right? So a success in this case is actually not owning a cell phone. So your success category is not owning a cell phone. Okay, so if you take a random sample of 200, you get a p hat. What does the sampling distribution of p hat look like? So again, we're thinking about all possible samples of size 200, right? So you've got a country, say maybe like 30 million people, and from those 30 million people, you take a sample of 200. How many different samples are possible? Well, the number is vast. It's huge possible number of samples here. So if we take all of those and we put them in a histogram, we would get a normal distribution probably, right? We would get the sampling distribution. So it would have a mean and a standard deviation. Okay, so what would the mean be? Well, the mean is equal to the population proportion. It should be about 28%, right? If 28% don't own a cell phone, then when you take a sample, and if you take lots of samples, you would expect them to be, bouncing around with 0.28, in the middle, right? And again, that's nothing new, right? It's this right here. The mean of the sampling distribution is the population proportion P. Nothing new or counterintuitive there. What about the spread? The spread is typically called standard deviation, but when we talk about point estimates like p hat, we give it a special name. We call that standard deviation the standard error. Why? It's not really to confuse you. We do that to actually clarify. It gives us a little more information. P hat is estimating P. That's the whole point of getting a P hat is so you can estimate P, right? So when it varies from P, it's actually an error, right? So how far it's varying from P is basically it's error, right? So the standard deviation tells us how much error there is, right? So we call it a standard error. And we have a formula for it. It's P1 minus P over N. Okay, so P here is 0.28, and we go 1 minus 0.28, and then we divide that by N. Here we're taking samples of size 200. Okay, so it's easy calculator work. Okay, then we're going to divide that by 200. We take the square root, get about a 3% standard error. So when your samples of size 200, you're expecting, the p hat to bounce within about 3% of 28%. So if you get 31%, no problem, right? If you get 27%, no problem. Nothing weird. But if you get 90%, something weird happened, right? If you get 1%, something weird happened, right? Because the standard error here is about 3%. So we go 0.032. Okay. All right. Now, is it normally distributed? Well, we have to make sure that 3 conditions have been met. Okay. So the first condition is it's a random sample. It says random. Okay. So it says random. 2, we have to make sure that the people are independent of each other. Why? Well, people who know each other tend to influence each other, and so you don't want all of your 200 adults coming from the same, small village in this country, right? Or, a small town or something, right? Or the same family, extended family, right? In, one part of the country, because those people will tend to influence each other, right? You want the people, basically independent of each other. And so the way we do that is we make sure that the sample is less than 5% of the whole population, right? So we want N to be less than or equal to 5% of the population size. So there's a problem here. We don't know the population of this country. We don't even know the name of this country, right? So what are we going to do? We're going to basically say, all right, let's solve for capital N and see how large of a population we would need to make 200 less than 5% of that value. So we back solve this inequality, divide through by the 0.05. Okay, so the 0.05 goes away. So we're going to have 200 divided by 0.05. So as long as the population in this country is more than 4,000, we should be good. I don't know about you, but I've never heard of a country that has fewer than 4,000 people in it, right? Can you think of anyone? Can you think of any country that has fewer than 5,000 or 4,000 people? I once had a student at this point mention the Vatican. Okay. Uh, but anyway, this should be fine, right? Every country in the world has more than 4,000 people in it. Okay. So the second condition has been met. What about the third condition? Well, we have to make sure that we have at least 10 people without a cell phone. That's the number of successes. We need to make sure that we get at least 10 of those. And we have to make sure that we get at least 10 people with a cell phone, the number of failures. Okay, so that's what these expressions do for us. N times P. So if 28% of adults in this country have cell phones and we have a sample of 200, how many, I'm sorry, did I say that backwards? If 28% don't own a cell phone, we have a sample of 200, how many do we expect to not have a cell phone? So we go 200 times 0.28, about 56. So we're expecting about 56 successes, 56 people without a cell phone. That's more than 10. What about failures, people with a cell phone? So we go 200, 1 minus 0.28, and that works out to be about 144. So we're expecting about 144 people to own a cell phone. So that's the number of failures, and that's more than 10. So with these 3 conditions met, we expect p hat to be normally distributed. Okay, and we have the mean and the standard error over there. Okay, let's see here. will we have any questions on the test where the sampling distribution won't meet all three? Oh, good question. I suppose I should tell you maybe there could be. All right. Most of the time, the three conditions will be met. Okay. But if we always made it so that they're always met, what would happen? You would probably stop checking, right? So there will be some in the homework where all three are not met. And actually, even on the exam, I do believe there are one or two questions um, during the course of the semester where the conditions have not been met. Okay. So most of the time they will be met, but every now and then there will be a time when they're not met. Does that answer your question, Crystal? Okay. So in other words, you have to check these things. And definitely on the exam, we'll be checking to make sure you're checking. And the reason why is because there's a tendency for people to just use the normal without checking the conditions. Okay. And these conditions are required for all of the math to work. Okay, so with the normal distribution, there are certain assumptions that are made, and if the assumptions aren't met, then all of the math can be really off. Okay, so we want to get you guys in the habit of checking these conditions. Okay, because probably at least some of you will actually study more stats in the future. Data science, data analytics is a big field now. So, at least some students who take this class will eventually become data analysts and data scientists. So we want you guys to get in the habit now of checking these conditions. Okay, good. So what is the probability that in a random sample of 200 adults, more than 30 do not own a cell phone? Okay, so you're going to take a sample and you're going to get a p-hat, right? You talk to each of these 200, you see if they own a cell phone or not. How likely is it that more than 30 do not own a cell phone? Well, this is something you can calculate, right? We can use our knowledge of the normal distribution to do that, right? So we know it's approximately normally distributed. So we can draw a normal. The middle is the 0.28. Okay, now the standard error is about 3%. So if I come over here to my inflection point, which conceivably could be about right there, that's going to be 0.31. So they're asking, what's the probability that p-hat is more than 0.3? Well, where's 0.3? 0.3 is about right there, right? If this is 0.28 and that's 0.31, then 0.3 is about right there, right? So they're saying, what is the likelihood that p-hat's going to be in there? Well, that's the proportion of the sampling distribution that's above 0.3. Okay, so just by looking, I would say it's probably about, I don't know, what do you guys think? Maybe 30%, maybe 25% of the distribution is over here. Certainly less than half, but still a pretty sizable proportion. So it's very possible that you could get more than 30% not owning a cell phone. It's not what you'd expect, but it wouldn't be unusual at all. So let's go from guessing to the actual value, right? So we use software for that. So we put in the mean, it's 0.28. We put in the standard error, which is the standard deviation, 0.032. And we say, what's the likelihood of being more than 30%? Okay, so do you see how that graph lines up with what I drew over here? Okay, so but it's better than what I drew, but so is the same general idea here. So 0.266 to the third decimal place. Okay, so this area here is 0.266. So you take a sample of 200 adults from this country, and you have about a 27% chance that more than 30% of people in your sample do not own a cell phone. This is really powerful stuff. I mean, if that's what you do for a living is you take samples, then this is really useful for you, right? Um, so let's interpret this a little bit. Okay. Let's say you're not the only economist or researcher studying, or maybe a sociologist or something studying this country. Maybe there are other people, right, that are studying this country. So let's say that you take a random sample of 200, and then there are other researchers out there that do the same thing. In fact, let's say that there's over time 100 different samples of 200 adults were obtained. Okay, so basically we've got tons and tons of these samples that have been taken, each one with 200 adults. How many of those samples would we expect to result in more than 30% not owning a cell phone? Well, if you do it 100 times, and there's a 0.266 chance of getting more than 30% not owning a cell phone, we could just multiply those two together. That gives us 26.6. We would expect about 27 of those samples to result in more than 30% not owning a cell phone. Okay, let's see. These are great example, but we do need to get to our confidence intervals here pretty quickly. So let's do one more part to this exercise, and then we're going to get back into confidence intervals. Any questions out there? Okay, well, let's say that you take a sample of 200 adults. What's the probability that between 25% and 30% do not own a cell phone? Okay, so where is 25%? I'm going to be lazy here and just kind of reuse this graph. 25% is about 3% below 28.28. So it'd be about right there. Okay, so we've got 0.25 there. So this is the proportion of the sampling distribution of p hats that falls between 0.25 and 0.3. Okay, so it's the proportion of all of the possible p hats out there that are between 0.25 and 0.3. So how likely would that be? I want one of you guys to do this. I want all of you guys to do it, and I want somebody to put it in the chat. I think you can do this now. We've done several of these examples. It's already in GeoGebra, these numbers. So if you've been following along with GeoGebra, you should be able to just click a couple of the buttons in GeoGebra to get the right answer at this point. Okay, what is the probability that in your sample of 200 that we get between 25% and 30% not owning a cell phone? Let's see here. Great. Crystal has it. Armand has it. That's exactly the right answer. Good. So how does it work? Well, we have the mean, we have the standard deviation. Now we just want to be between two values. So I can set this up with the between bracket choice there. So we go 0.25, and then we're going to go 0.3. And again, this picture lines up with what I drew over here. It's better than what I drew, but it's kind of the same idea, right? And then so you look over here and you get 0.5598. Okay, so the probability that your p hat is between 25% and 30% is about 0.5598, about a 56% chance. So it's pretty likely. It would be expected that your sample is somewhere between 25 and 30%. Would it be unusual? Okay, let's see here. So let's do this last one too, just for good measure, and then we will get back into our confidence intervals. Would it be unusual for a random sample of 200 adults in this country to result in 50 or fewer who do not own a cell phone? Why? Okay, well, what do we mean by unusual? That sounds a little bit subjective, right? So You might look at an example and say, hey, that's unusual. Somebody else might say, no, it's not unusual, right? So we have a rule of thumb for unusual, and that is 5%. So if something has less than a 5% chance of happening, we'll typically call that unusual. Okay, now that's just mostly for our class. Other fields, other disciplines, they might have a slightly different definition for unusual, but for this semester we'll use 5%. So if 50 or fewer don't have a cell phone out of the 200, what kind of p hat would that be? Well, that's 1/4, which is 0.25. So this is just a slightly different way of asking, what's the probability of p hat being less than or equal to 0.25? Again, I'm just going to be lazy and use my graph from up here. I already have 0.25 on there. So what's the likelihood of being down in this region up over here? Well, that graph isn't great, but it's not too bad either. I can kind of look at that and get a ballpark idea. I don't know, maybe 20%. Okay. But we don't need to guess. We can actually use GeoGebra, right? So we go over to GeoGebra and we say, okay, the probability of being less than 0.25, and we get it. It's actually more like 17%. Okay, so 0.174. And so what is that saying? Well, it's saying we take your sample of 200, and how likely would it be that you get fewer than 25% not owning a cell phone? Well, there's about a 17% chance of that happening. So it's not unusual. It's not likely, but it's not what you'd expect, but it wouldn't be shocking, right? So it's not unusual because 0.174 is more than 0.05. Things with a 17% chance of happening happen all the time. I mean, it's very, very possible. Okay, great question, Killian. How do we do these on the test where we don't have software? Exactly. I actually addressed that very question in an announcement because it's a common question I get. All right. What we do is we use screenshots. Okay. So you remember on the first exam where you answered the question about the randomization applet? You didn't have the computer there, right? How did you answer it? Well, we gave you a picture from the screenshot from the software, right? So basically, the same kind of thing will work with the GeoGebra. We'll have screenshots of GeoGebra output that you'll interpret on the exam. Does that kind of make sense? So it's basically like it did we did on the first exam. We'll use screenshots from the software. So to get a more concrete idea of that, I have some problems here, some example test 2 problems that involve GeoGebra along with a key. So you can kind of see how this, get a more concrete idea of how that'll work. Why did we do this? Well, the only other way of doing this is if you guys had graphing calculators. So basically, before 4 or 5 years ago, we made students buy a graphing calculator so they could do more on exams, right? And the problem is that those calculators cost like $100. And so we wanted to save you guys some money and not have to buy those graphing calculators. So this is kind of our compromise for that. Does that answer your question, Killian? And then so is question 2 similar? Is exam 2 similar question layout? Yeah, there'll be about 12 to 15 questions on exam 2, and a few of them will involve GeoGebra, inputs and outputs. So we'll have some screenshots from GeoGebra. It won't be like for every problem, but on maybe 3 or 4 of the problems, you'll have some GeoGebra screenshot. Okay, so yeah, to get a more concrete idea of that, come over here to this announcement that I put in over on Canvas and look through those examples, and then I think very quickly you'll get the idea. All right, so how do we use this idea of the sampling distribution of p hat? Well, we use it to make our confidence intervals. Okay, so if we were to scroll back to a couple of sections ago, we would have this formula here, p hat plus or minus z star, the critical z-score, times the standard error. We looked at that formula back a couple of sections ago. Well, now we know what the standard error is. It's this. Okay, so we actually have a formula now for confidence intervals. Okay, so what we do is we take our point estimate, which in this case is p hat, then we add and subtract a margin of error. So what makes up the margin of error? Well, it comes down to your standard deviation, your standard error. Okay, so we have our standard error, and then depending on if we want more confidence or less confidence, we adjust z star. So I encouraged you last time to think of z star as like a dial. You can increase it or decrease it depending on how much confidence you want to have. Okay, so there's a formula. Okay, so the goal in 3.5 is to be able to use this formula, okay, and to have a a nice idea of how the confidence interval works and to be able to actually calculate it. Okay, so before we do the arithmetic on it, let's try to think of kind of intuitively how the confidence interval works. Okay, so I think it's pretty intuitive. If you want to increase your confidence level, you have to increase the width of the confidence interval. And the reason why is because of, well, you can think of the confidence interval like a one-dimensional net that you're throwing on the number line to capture P. If you want to be more confident of capturing your target, you would typically make your net larger, right? So if you want to increase the confidence level, you have to increase the width of the confidence interval. Now that's actually reflected in the formula. If this is the margin of error, then as your confidence goes up, right, your number of standard deviations goes up, right? So we can actually see it there in the formula. Also, pretty intuitively, if you increase the sample size, it will decrease the width of the confidence interval. That's also reflected in the formula. If you look in the denominator here, we see n. As you make n larger and larger, you're dividing by a larger number. It actually makes the margin of error smaller. Okay, so increasing the sample size will decrease the width of the confidence interval. Okay, so we have 7 minutes here. I want you guys to try one of these. So at the bottom of 96, I want you to use intuition. I want you to use the idea of a net. And if you want to, you can even use the formula above to help you answer these questions here. So what is this regarding? We're doing some educational research. Okay, so there are researchers who spend most of their career looking at education. Okay, and one topic within education is literacy. And so kindergartners, some can read and some can't. Okay, so kindergarten, they're pretty young, maybe 4, 5, 6, right? 5 or 6. So not all 5 or 6-year-olds can read. It's not like they don't have universal literacy basically in kindergarten, right? And so, but they do have a good idea about what percent of kindergartners can read. It's about 27%. I'm sorry, in our sample, it was about 27%, right? So we're taking a sample of 100 kindergartners, and in that sample, 27% can read. Okay, so that's our p hat because that's coming from a sample. So from that, we can calculate a 95% confidence interval. And again, we're not quite ready to do the calculation ourselves. We're almost there, but so I'll do the calculation here. It's 0.18 up to 0.37, 0.357. And we know the interpretation, right? It means we're 95% confident that the proportion of all kindergartners who can read is captured by the interval from about 18% up to 36%. In other words, the percent of kindergartners who can read could be as low as about 18% or about as high as 36%. What I want you to do now is to change the scenario a little bit. Instead of 95% confidence, I want you to do 99% confidence, or 95 or 90% confidence. Instead of 100 in your sample, do a sample of 150. Okay, instead of a sample of 100, do a sample of 75. And then intuitively, without really lifting your pencil off the paper, I want you to tell me if it's going to be wider or narrower. Okay, how does it affect the width of the confidence interval? Okay, so circle either wider or narrower for all of these, and then we'll be almost out of time here. But we'll be basically right at the threshold of being able to calculate our own confidence interval. So who can tell us the first one? If we switch from a 95% confidence level to a 99% confidence, do we have to make the interval wider or narrower? Anybody? Wider. Yeah, exactly. Great. Use the idea of a net. If you want to be more confident that you're going to capture the target, all of the things being equal, you would tend to make the net larger, right? Okay, so if we want to reduce the confidence level, wider or narrower? Narrower, yeah, for the same reason. Now, why would we ever want less confidence? Well, what you'll find is that these things can be expensive, right? I mean, it takes money and time to contact people. So, you might be okay with a lower level of confidence if if that's what your budget allows for, right? So anyway, sometimes we'll settle for a lower confidence level. Kind of depends on what field you're in and what kind of work you're doing. Okay, what if we increase the sample from 100 to 150? Any ideas there? It'd make it narrower. Great. So you guys are definitely picking up on this, I think. And you can understand this by thinking about information. Okay, if you have more people in your sample, then you have more precision, right? You have more data, right? You have more information. So that should result in a better confidence interval. Okay, all of the things being equal, do we want a wider interval or a narrower interval? Well, we like narrower because that's more precision, right? So yeah, by increasing the sample size, you actually make the interval narrower, which is a good thing, right? You get a more, a better idea of what your target is. Okay, so if you, instead of using 100, you had a smaller sample, then that would make the interval wider. And by the way, if your intuition fails you, you can actually just calculate the formula, right? You got the formula there, so you can just calculate it and see, hey, did it make it wider or narrower? Okay, and then to finish off here, these last two are a little, it's harder to think intuitively here. So what I'll leave you with here is, okay, if you look at this formula, the most that this value can be, if we just look on the inside here, the most that can be, I'm sorry, the very top part, the most that this can be is 0.25. And I can prove that with a little algebra. If you want to sit down with me after class, I can prove this to you that the most that quantity can be is 0.25. And that occurs when p hat is 0.5. Okay, so the closer your p hat is to 0.5, the larger the interval will be. The further from 0.5 you are, the smaller the interval will be. So how does that help us? Well, here's 0.5. The closer your p hat is to that, the wider the wider the interval will be. Okay, so we had 0.27 in our sample. Well, what if it had been 0.42? Well, 0.42 is closer to 0.5. So that would result in a wider interval. Okay. What if instead of 27%, it had been 18%? Well, 18% is further from 0.15. So that would result in a narrower confidence interval. Okay. All right. So there's a lot of material today, but we did it. I mean, we basically got through everything we needed to. Maybe we're one page behind, but it's not too bad. So we'll be in a good spot for next time. We're really ready to actually calculate these confidence intervals by hand. We understand the theory behind it. We understand the formulas. And now we're ready to really actually calculate one by hand. Okay, so that's the next example that we'll pick up with on, well, let's see, I guess on Tuesday, huh? We're done for the week. So that's it for today. Are there any questions out there that you guys want to go over?